Hello friends, welcome to my lecture on application of probability theory to queuing theory and reliability theory. Queuing theory is the mathematical study of waiting lines or queues. A queue or waiting line is formed when units that is customers or clients requiring some kind of service arrive at a service counter or service channel. A simple queuing model is shown in the following figure. There you can see arrivals, queue is formed and then service is done and then they depart. So, basic characteristics of a queuing system are the input or arrival pattern, the service mechanism or service pattern, the queue discipline, the system capacity. Let us discuss all these characteristics one by one. So, input or arrival pattern, the input describes the manner in which customers or units arrive and join the queuing system. It is not possible to observe or detect the actual amount of customers arriving at the queue for service. Hence, we express the arrival pattern of customers by the probability distribution of the number of arrivals per unit of time or of the inter arrival time. Let us consider those queuing systems in which the number of arrivals per unit of time is a Poisson random variable with mean lambda. We know that in this case the time between consecutive arrivals, that is the inter arrival time of the Poisson process, has an exponential distribution with mean 1 by lambda. Now, let us discuss service mechanism. It can be described by a service rate, that is the number of customers serviced in one time period, or by the inter service time, that is the time required to complete the service for a customer. Let us consider those queuing systems in which the number of customers serviced per unit of time has a Poisson distribution with mean mu, or equivalently the inter service time has an exponential distribution with mean 1 by mu. Now, next we consider queue discipline. In this procedure, the customers are selected for service when a queue is formed. The various types of queue disciplines are tabulated in the following table. Number 1, FIFO or FCFS. FIFO means first in first out or first come first served. This is the most commonly used procedure in servicing customers. Number 2, LIFO or LCFS, last in first out or last come first served. This procedure is used in inventory systems. SIRO, SIRO, selection for service in random order. This is not very usual. PIR, priority in selection, that is customers are prioritized upon arrival. This procedure is used in manual transmission managing systems. If a message is very important, it is transmitted first, it is given priority over other messages. So, it is priority in selection. Now, let us assume that service is provided by the FCFS or FIFO procedure, that is on a first come first served basis. So, the maximum number of customers, system capacity, the maximum number of customers in the queuing system can be either finite or infinite. In some queuing models, only limited customers or units are allowed in the system. Now, let us talk about transient and steady states. A queuing system is said to be in transient state when the operating characteristics of the system depend on time. A queuing system is said to be in steady state when the operating characteristics of the system are independent of time. For example, if P and T is the probability that there are n customers in the system at time t, when t is greater than 0, finding P and T is quite a difficult task even for a simple case. Thus, we are most interested in the steady state analysis of the system, that is in determining P and T in the long run, that is as t goes to infinity. Thus, we look for steady state probability, that steady state probabilities, that is P and T goes to P n a constant as t goes to infinity. Now, let us discuss Kendall's notation of a queuing system. In Kendall's notation, Kendall gave this notation in 1951. So, queuing system has this form A oblique B oblique C such that D by E, where A is inter arrival distribution, B is service time distribution, C is number of channels or servers, D is system capacity, E is queue discipline. Now, A and B usually take one of the following symbols: M for Markovian or exponential distribution, G for general distribution, and D for fixed or deterministic distribution. The four important queuing systems described in Kendall's notation are as follows: MM1 infinity oblique FIFO, MMS infinity oblique FIFO, MM1 K oblique FIFO, MMS K oblique FIFO. Okay. We will be discussing the in this lecture we will be discussing the first queuing system MM1 infinity oblique FIFO. Next we define the line length and queue length for a queue. So, for a queue the line length or queue size is defined as the number of customers in the queuing system. Also the queue length is defined as the difference between the line length and the number of customers being served, that is queue length is equal to line length minus number of customers being served. Now, we will be using the following terminology: N is the number of customers units in the system, NT number of customers in the system at time t, PNT the probability that there are exactly n customers at time t, that is probability that NT is equal to n, Pn the steady state probability that exactly n customers are there in the system, and then lambda n is the mean arrival rate. Okay, mean arrival rate when there are n customers in the system, mu n is the mean service rate when there are n customers in the system, lambda is mean arrival rate when lambda n is constant for all n, and mu is mean service rate when mu n is constant for all n. Now, let us some more notations are there. Rho is equal to lambda by mu, which is known as utilization factor or traffic intensity. FSW is the probability density function of waiting time in the system. FQW is the probability density function of waiting time in the queue. LS is the expected number of customers in the system or the average line length. The LQ is the expected number of customers in the queue or the average queue length. LW is the expected number of customers in the non-empty queues. WS is the expected waiting time of a customer in the system. WQ is the expected waiting time of a customer in the queue. Now, let us find the differential equations for the transient state probabilities for the Poisson queue systems, which are also known as birth death process or immigration process. Let NT be the number of customers in the system at time t, and PNT be the probability that there are n customers in the system at time t, where n is greater than or equal to 1, that is PNT equal to probability that NT equal to n. Then the differential equations satisfied by PNT are given by Pn dash t, that is derivative of PNT with respect to t is equal to minus lambda n plus mu n into PNT plus lambda n minus 1 into Pn minus 1 t plus Pn mu n plus 1 Pn plus 1 t, where n is greater than or equal to 1, and when n is equal to 0 we have the differential equation P naught dash t equal to minus lambda naught P naught t plus mu 1 P1 t. Transient state probabilities for Poisson queue systems. The solution of these differential equations, the solution of the two differential equations that we have got, number 1 and 2. Number 1 is for n greater than or equal to 1 and number 2 is for n equal to 0. So, the solution of these differential equations yields the transient state probability PNT for n greater than or equal to 0, but this is exceedingly difficult even for simple problems. So, we consider steady state probabilities for Poisson queue systems. The steady state probabilities for Poisson queue systems are derived by assuming that PNT goes to Pn independent of t as t tends to infinity. The equations of steady state probabilities Pn can be obtained by putting Pn dash t equal to 0, because Pnt is now as t tends to infinity is a constant. So, when derivative of Pnt will be, so when we take the derivative of Pnt with respect to t, it will be equal to 0. So, Pn dash t equal to 0 and replacing Pnt by Pn in equations 1 and 2, and then we obtain, you can see here, if you put Pn dash t equal to 0 and Pnt equal to Pn, then you get minus lambda n plus mu n into Pn plus lambda n minus 1 into Pn minus 1 plus mu n plus 1 into p n plus 1 equal to 0. Okay. So, we have this equation, this one, okay. And similarly, the other equation number 2 for n equal to 0 becomes p naught dash t equal to 0, and this is minus lambda naught p naught plus mu 1 p 1, okay, at the right side. So, we get minus lambda naught p naught plus mu 1 p 1 equal to 0. So, we get this second equation. Now, so from these equations one can determine the values of p n in terms of p naught and the value of p naught. Now, let us see, equations 3 and 4 are called the valence equations. This equation 3 and 4, okay, this 3 and this 4 are called valence equations or equilibrium equations of the Poisson Q systems. Using the principle of mathematical induction, it can be shown that this p n from this equation, okay, using the process of mathematical induction, principle of mathematical induction, one can show that p n equal to lambda naught into lambda 1 into lambda 2 and so on lambda n minus 1 divided by mu 1 mu 2 mu 3 mu n into p naught, and p naught is equal to 1 over 1 plus sigma n equal to 1 to infinity lambda naught lambda 1 lambda 2 lambda n minus 1 divided by mu 1 mu 2 mu 3 and so on mu n. Now, let us consider the model MM1 infinity oblique FIFO single server with infinite capacity. So, here A is M, B is also M, that means we are considering exponential type distribution. Number 3, one means we are considering single server, okay. Infinity means there is Q can be infinite, okay, and FIFO means we are considering the discipline as first come first served, first in first out, okay, first in first out FIFO, okay, that is the Q discipline we are considering. A is inter service arrival distribution, B is service time distribution, both we are assuming as that they follow exponential type distribution. C is the number of channels or servers, so we are considering that the system has one server, okay, and D is the system capacity we are taking as infinite. So, we have MM1 infinity FIFO model, okay. For this model we make the following assumptions: the mean arrival rate is constant, that is lambda n equal to lambda for all n, mean service rate is constant, that is mu n equal to mu for all n, mean arrival rate is less than the mean service rate. So, that means lambda is less than mu, or we can say rho equal to lambda by mu is less than 1, rho is the traffic density. So, the traffic density we are assuming that it is less than 1, and which will ensure that an infinite queue will not build up, because service rate is higher than the mean service rate is higher than the mean arrival rate. So, the infinite queue will not build up. Now, under assumption C, that is mean arrival rate is less than the mean service rate, okay, the equation 6 simplifies to, let us see equation 6, this equation 6 will become 1 over 1 plus sigma lambda naught lambda 1 lambda 2 lambda n minus 1 are all equal to lambda. So, we have lambda over mu raised to the power n, okay. So, we get 1 over 1 plus sigma n equal to 1 to infinity lambda by mu to the power n, which is 1 over 1 plus lambda by mu plus lambda mu by mu whole square and so on, which is geometric series with ratio 1 lambda by mu. So, we have the sum of the series as 1 minus lambda by mu to the power minus 1. So, 1 upon 1 minus lambda by mu to the power minus 1 is 1 minus lambda by mu, and lambda by mu we denote by rho, okay. So, P naught is equal to 1 minus rho. Now, let us consider the case substituting equation 7 into 5, okay. So, this 7 P naught equal to 1 minus rho, let us put in equation number 5. Equation number 5 now is P n equal to the lambda by mu to the power n equal to P naught, okay, because we are assuming that the mean service rate and the mean arrival rate are constant, okay. So, we have P n equal to lambda by mu raised to the power n into P naught, okay, and this is rho to the power n, and P naught is 1 minus rho. So, we have P n equal to rho to the power n into 1 minus rho. Now, characteristics of model 1. Okay. So, average are expected number of customers in the system. Average are expected numbers of number of customers in the system we denote by LS. So, if n denotes the number of customers in the queuing system, then n is a discrete random variable. It will take value 0, 1, 2, 3 and so on, and we know that P n is the probability that n takes the value n. Okay. So, it is equal to rho to the power n into 1 minus rho, as we have seen just now, for n equal to 0, 1, 2, 3 and so on. Now, thus the expected number of customers in the system is LS is given by expected value of n, that is sigma n equal to 0 to infinity n P n, which is sigma n equal to 0 to infinity n into rho to the power n 1 minus rho. Now, when n is equal to 0, first term is 0. So, we can write it as 1 minus rho is independent of n. So, we can write it outside, and then sigma n equal to 1 to infinity n rho to the power n. Now, LS can also be written as rho times 1 minus rho into sigma n equal to 1 to infinity n times rho to the power n minus 1. So, we have sigma rho into 1 so we have rho into 1 minus rho, and then this series sigma n equal to 1 to infinity n rho to the power n minus 1 becomes 1 plus 2 rho plus 3 rho square and so on. Okay. And its sum we know it is equal to 1 minus rho to the power minus 2. Okay. So, we have rho into 1 minus rho to the power minus 1, and therefore, LS is equal to rho upon 1 minus rho. Now, rho is lambda by mu. So, we can put the value of rho as lambda by mu, and we get LS equal to lambda over mu minus lambda. So, this means that average or expected number of customers in the system is equal to lambda over mu minus lambda. Now, average or expected number of customers in the queue or average length of the queue. We know that queue length is given by line length minus number of customers being served. Thus, if the number of customers in the system is n, then the number of customers in the queue or the queue length is n minus 1. Hence, the expected length of the queue is LQ equal to E n minus 1, and so it is sigma n equal to 1 to infinity n minus 1 into P n. Okay. Now, when n equal to 1, the first term becomes 0. Okay. So, and so this or before that, what we can do is we can put the value of P n. P n is rho to the power n into 1 minus rho. So, this summation becomes sigma n equal to 1 to infinity n minus 1 into 1 minus rho into rho to the power n, and therefore, using the fact that at n equal to 1 the first term becomes 0, n will start with 2 onwards. So, n equal to 2 to infinity n minus 1 minus rho into rho to the power n, and here what we can do is let us put m equal to n minus 1. So, that m runs from 1 to infinity, and we have m times 1 minus rho into rho to the power m plus 1, and therefore, I can write LQ equal to rho square times 1 minus rho into sigma m equal to 1 to infinity m times rho to the power m minus 1. Okay. And this we know the sum of this is 1 minus rho to the power minus 2. So, we have rho square into 1 minus rho to the power minus 1, and therefore, LQ which is the average or expected number of customers in the queue is equal to rho square upon 1 minus rho. Rho is lambda by mu. So, lambda by mu whole square upon 1 minus lambda by mu, which gives us LQ as lambda square upon mu into mu minus lambda. Now, let us consider the case average or expected number of customers in non-empty queue. So, this means that LW is the expectation of n minus 1, n minus 1 is the line length, okay, divided by q n minus 1 LW equal to expectation of n minus 1, given that n minus 1 is greater than 0, that is the queue is non-empty, okay, at least one customer is there. Okay. So, n minus 1 is greater than 0, and therefore, expectation of n minus 1, okay, expectation of n minus 1 n is no LW equal to expectation of n minus 1, given that n minus 1 is greater than 0. N is the number of customers and denote the number of customers in the Q system. So, number of customers is greater than 1. Okay. So, expectation of n minus 1 divided by probability that n minus 1 is greater than 0, and we know that expectation of n minus 1, that is LQ, okay, is equal to rho square upon 1 minus rho. Okay. LQ is equal to rho square upon 1 minus rho. So, we have and P n minus 1 greater than 0 is equal to 1 minus P naught minus P 1. P naught means probability that n is equal to 0, and P 1 is the probability that n equal to 1. So, probability that n is greater than 1 can be obtained from 1 minus P naught minus P 1. So, 1 minus P naught is equal to 1 minus rho, and P 1 is equal to rho times 1 minus rho, because P n is equal to rho to the power n into 1 minus rho for all n greater than or equal to 1. So, we have on simplifying this we get rho square. Okay. So, P n minus 1 greater than 0 is rho square. So, L w equal to rho square upon 1 minus rho divided by rho square, which is 1 over 1 minus rho, and that is equal to mu upon mu minus lambda, as rho equal to lambda by mu. Now, let us discuss the probability that number of customers in the system exceeds k. Okay. So, probability that number of customers in the system exceeds k, that is n is greater than k. Now, this is equal to sigma n equal to k plus 1 to infinity P n equal to k plus 1 to infinity, the value of P n is rho to the power n into 1 minus rho. We can write it as rho to the power k plus 1 into 1 minus rho into sigma n equal to k plus 1 to infinity rho to the power n minus k minus 1, and this is rho to the power k plus 1 into 1 minus rho, and we can put m as n minus k minus 1. When you take m equal to n minus k minus 1, then this summation becomes sigma m equal to 0 to infinity rho to the power m, and hence probability that n is greater than k is equal to rho to the power k plus 1 into 1 minus rho, and this is geometric series with geometric ratio rho. So, its sum is 1 over 1 minus rho. So, we get 1 minus rho to the power minus 1, and this will give you on simplification that probability that n is greater than k equal to rho to the power k plus 1, that is lambda by mu to the power k plus 1. So, this is the probability, lambda by mu to the power k plus 1 is the probability that number of customers in the system exceeds k. Now, let us discuss probability density function of the waiting time of a customer in the system, be denoted by FSW. So, let Ts be the random variable that represents the waiting time of a customer in the system, FSW be the probability density function of Ts, and FSW given n be the probability density function of Ts, given that there are already n customers in the system when the customer arrives. Then FSW is given by mu minus lambda into e to the power minus mu w into sigma n equal to 0 to infinity lambda w raised to the power n divided by n factorial. Now, the sum of this series we are all aware, the sum of this series is e to the power lambda w. So, we get mu minus lambda e to the power minus mu w into e to the power lambda w, where w is greater than 0. Thus, the probability density function of the waiting time of the customer in the system is FSW equal to mu minus lambda into e to the power minus mu minus lambda into w, where w is greater than 0. This is the probability density function of the exponential random variable with parameter mu minus lambda. Now, the distribution function, we know distribution function FSW is equal to probability that Ts is less than or equal to w. So, when w is less than 0, okay, when w is less than 0, because we know that FSW is the probability density function of the random variable. This is equal to mu minus lambda into e to power minus mu minus lambda w when w is greater than 0. So, when w is less than 0, okay, probability is 0. So, we get FSW equal to 0. So, 1 minus and when w is greater than or equal to 0, this FSW is equal to integral over 0 to infinity FSW 0 to w because we want the probability that Ts is less than or equal to W. So, integral over 0 to W Fsw dW, Fsw dW, and this will be equal to integral 0 to infinity Fsw is mu minus lambda into e to the power minus mu minus lambda W dW, okay, and this is nothing but minus e to the power minus mu minus lambda into W 0 to W. So, this is equal to 1 minus e to the power minus mu minus lambda W, okay. So, this is the distribution function of Ts. Now, average or expected waiting time of a customer in the system. So, the waiting time of a customer in the system is the random variable Ts, which is exponentially distributed with parameter mu minus lambda as given in equation 9 here, okay, mu minus lambda. So, thus the average waiting time of the customer in the system is 1 over mu minus lambda, because it follows exponential distribution. Okay. Now, the probability that the waiting time of a customer in the system exceeds T. So, probability that Ts is greater than T is integral over W equal to T to infinity Fsw dW. Fsw is mu minus lambda into e to power minus mu minus lambda into W. So, on integration we get probability that Ts is greater than T equal to e to the power minus mu minus lambda into T. So, this is the probability that waiting time of a customer in the system exceeds T. Probability density function of the waiting time of a customer in the queue FQW is equal to is given by this. The probability density function of the waiting time of a customer in the queue is Fsw equal to lambda by mu minus lambda into e to the power minus mu minus lambda into W for W greater than 0, 1 minus lambda by mu, okay, for W equal to 0 and 0 for W less than 0. The distribution function of the waiting time of the customer in the queue is FQW, which is probability that TQ is less than or equal to W, and TQ we have seen, okay, probability that TQ is less than or equal to W. So, TQ is, we have defined TQ earlier. Fsw is the probability density function of Ts, where Ts is the random variable that represents the waiting time of a customer in the system, and TQ denotes the random variable that represents the waiting time of a customer in the queue, okay. So, this is the probability density function of the waiting time of the customer in the queue, okay, where TQ is the random variable which denotes the waiting time of a customer in the queue. So, Fsw is given by this, and then we have, this is not Fsw, this is FQW, okay. So, this is FQW. FQW is given by these values, okay. FQW equal to lambda by mu minus lambda e to the power minus mu minus lambda into W for W greater than 0, 1 minus lambda by mu for W equal to 0 and 0 for lambda W less than 0, okay. And then the distribution function of the waiting time of the customer in the queue is given by FQW, where probability that TQ is less than or equal to W. So, this can be, these are given by 0 when W is less than 0, 1 minus lambda by mu when W equal to 0, 1 minus lambda by mu plus lambda by mu e to the power minus mu minus lambda into W for W greater than 0. We can easily obtain these values, because FQW is equal to integral over minus infinity to W FQW dW, okay, and FQW we have here, FQW is 0 when W is less than 0, okay. So, this will go to 0 to W FQW dW, okay. So, from here we can easily find these values. Now, the probability that the waiting time of a customer in the system exceeds T. Here 0 to W, when W is greater than 0, we can put the value of FQW, okay. FQW for W greater than 0 is given by this expression, okay, lambda by mu into mu minus lambda e to the power minus mu minus lambda into w. So, when you integrate this, okay, we will get lambda by mu into 1 minus e to the power minus mu minus lambda into w. Okay. So, we will get this if you integrate this 0 to w f q w d w. Okay. What we will get 0 to w lambda by mu into mu minus lambda e to the power minus mu minus lambda into w dw, and this will be lambda by mu. Here we will have minus e to the power minus mu minus lambda into w 0 to w. So, we will get this as lambda by mu into 1 minus e to the power minus mu minus lambda into w. Okay. So, that is the formula for probability that TQ is less than or equal to W. Now, probability that the waiting time of a customer in the system exceeds T, okay, probability that TQ is greater than T. So, this is equal to integral T to infinity FQW dW, and FQW dW is lambda by mu minus lambda e to the power minus mu minus lambda w dW. So, this is lambda by mu, and this quantity is the derivative of minus e minus mu minus lambda into w. Okay. So, probability that TQ is greater than T is lambda by mu times minus e to the power minus mu minus lambda into dw into w, integral over the limits are T to infinity. So, lambda by mu, now this goes to 0 when the w goes to infinity. So, this is 0, and when you put the lower limit you get 0 plus e to the power minus mu minus lambda into T. So, we get mu minus lambda into e to the power, we get lambda by mu into e to the power minus mu minus lambda into T, lambda by mu into e to the power minus mu minus lambda into T. Okay. Now, the average waiting time of a customer in the queue WQ is given by lambda over mu into mu minus lambda. The average waiting time of a customer in the queue if she has to wait is given by E expectation of TQ, where TQ is greater than 0. Expectation of TQ is nothing but WQ, and TQ greater than 0 is 1 minus P TQ equal to 0. Now, expectation of TQ there given TQ greater than 0 is then WQ equal to lambda over mu times mu minus lambda, and probability that TQ equal to 0. Okay. Probability that TQ equal to 0 we have seen here, probability that TQ equal to 0, okay, is equal to 1 minus lambda by mu. Okay. Probability that TQ equal to 0 is equal to 1 minus lambda by mu. So, 1 minus this is WQ divided by 1 minus lambda by mu, and this gives you WQ divided by lambda by mu, but WQ equal to lambda by mu into mu minus lambda divided by lambda by mu. So, this is equal to 1 over mu minus lambda. So, we get this. Now, let us discuss Little's formulae for the MM1 infinity FIFO model. The relations between LS, LQ, WS and WQ are given as follows: LS equal to lambda WS, LQ equal to lambda WQ, WS equal to WQ plus 1 by mu, LS equal to LQ plus lambda by mu. So, first let us see LS equal to lambda WS. Okay. We know that LS is equal to WS is 1 over mu minus lambda, LS is what? LS is lambda over mu minus lambda. Okay. Yeah, LS is lambda over mu minus lambda, WS is equal to 1 over mu minus lambda. Okay. So, these two relations imply that LS is equal to lambda times WS. Okay. So, this is how we get the first formula Ls equal to lambda Ws. Now, let us look Lq and Wq. Let us look at Lq. Lq is equal to lambda square upon mu into mu minus lambda. Okay. So, Lq equal to lambda square upon mu into mu minus lambda. Okay. And Wq is lambda over mu times mu minus lambda. So, Lq equal to lambda times Wq. Okay. So, Lq equal to lambda times Wq. Now, let us show that Wq plus 1 by mu, Wq plus 1 by mu, Wq plus 1 by mu equal to Wq is equal to lambda over mu times mu minus lambda. So, this is equal to 1 by mu lambda plus mu minus lambda divided by mu minus lambda. So, this is 1 over mu minus lambda, and 1 over mu minus lambda is Ws. Ls is this, Ws is here, Ws is 1 over mu minus lambda. So, this is Ws. Okay. And then Lq plus 1 by Lq plus lambda by mu, Lq is equal to lambda square over mu times mu minus lambda, that is the value of Lq plus lambda over mu. So, this is lambda over mu times lambda over mu minus lambda plus 1, and we get here lambda over mu lambda plus mu minus lambda, that means mu upon mu minus lambda. So, we cancel it and we get lambda over mu minus lambda, and lambda over mu minus lambda is Ls. Okay. Ls, lambda over mu minus lambda. So, if one parameter, if Ls or Ws or Lq or Wq, one is known, the other three can be found from Little's formulae. So, they are very useful. This is the proof. Now, so the Little's formulae are very useful in the study of MM1 infinity FIFO model, because if any of the quantities Ls, Lq, Ws, Wq are available, then the other three can be readily obtained from Little's formulae, which are given in the above theorem. Now, let us look at the first question. What is the probability that a customer has to wait more than 15 minutes to get his service completed in MM1 FIFO queue system, if lambda equal to 6 per hour and mu equal to 10 per hour. Okay. So, we are given the mean service rate, that is mu equal to 10 per hour, and mean arrival rate lambda equal to 6. Okay. Now, let us see which formula gives us the probability that a customer has to wait more than 15 minutes to get the service. Okay. So, let us go to that formula. So, this is the probability that the waiting time of a customer in the system exceeds T. Okay. So, if the system the customer has to wait more than 15 minutes, then probability that Ts is greater than or equal to 15 we have to find. So, we have probability that Ts is greater than T. Okay. So, we have a probability that Ts is greater than T is equal to e to the power minus mu minus lambda into T. So, this is equal to e to the power minus mu is 10, lambda is 6 into T. So, we get e to the power minus 40. So, the if the system if the customer has to wait for more than T in minutes, then probability is Ts greater than T. Now, here we want the probability that the system that the customer has to wait more than 15 minutes. Okay. So, T here T is equal to 15. Okay. So, probability that Ts is greater than 15. Now, 15 we have to convert into hours. So, 1 by 4 hours. So, probability that Ts is greater than 1 by 4 is equal to e to the power minus 4 into 1 by 4, which is equal to e to the power minus 1. Okay. So, the probability that the customer has to wait more than 15 minutes to get the service is e to the power minus 1. Now, consider an MM1 queuing system, find the probability that there are at least n customers in the system. So, number of customers are greater than or equal to n. Let us go to that formula. Probability that number of the customers in the system exceeds k. Okay. So, probability that the number of customers in the system exceeds k is given by this formula, probability that n is greater than k. Okay, sigma n equal to k plus 1 to infinity p n, okay, and p n is rho to the power n into 1 minus rho. So, let us go to that formula. So, we want the probability that there are at least n customers. So, probability that nt is greater than, probability that n is greater than or equal to n, n is greater than or equal to n. So, probability that sigma k is equal to n to infinity probability pk. Okay. So, this is equal to sigma k is equal to n to infinity rho to the power k into 1 minus rho. Okay. So, we will have rho to the power n into 1 minus rho we can write outside, and here we will have k equal to n to infinity rho to the power k minus n, and k minus n we can write as some equal to I. Then this is sigma this is rho to the power n into 1 minus rho into sigma I equal to 0 to infinity rho to the power I. So, we will have rho to the power n into 1 minus rho, and this is 1 over 1 minus rho. So, this will be equal to rho to the power n, and rho is equal to lambda by mu. Okay. So, lambda by mu raised to the power n. So, probability that there are at least n customers in the system is given by lambda by mu raised to the power n. Now, consider an MM1 queuing system. If lambda equal to 6, mu equal to 8, find the probability of at least 10 customers in the system. So, we have just now found the probability that there are at least n customers in the system. So, let us take n equal to 10 here. Okay. So, we have probability that n is greater than or equal to 10 is equal to lambda by mu raised to the power 10, and lambda is equal to 6, mu is equal to 8 raised to the power 10. So, this is 3 by 4. So, this is 0.75, 0.75 raised to the power 10, and this comes out to be 0.0563. Okay. Now, let us consider another problem. In a given MM1 queuing system, if lambda equal to 12 per hour, mu equal to 24 per hour. So, mean service rate is 24 per hour and mean arrival rate is 12 per hour. Find the average number of customers in the system. So, let us find the formula for the average number of customers in the system. So, average or expected number of customers in the system is given by LS, and LS equal to lambda over mu minus lambda. So, we will apply this formula. So, average number of customers in the system is given by LS, which is lambda over mu minus lambda. So, LS is equal to lambda over mu minus lambda, and lambda is equal to 12, okay, 12 per hour, mu equal to 24 per hour. Okay. So, we have 24 minus 12. So, this is 12 divided by 12, and we have 1 here. Okay. Because this is a service rate, this service rate per hour. In 1 hour, the arrival rate is 12, and in 1 hour the service rate is 24. Okay. Now, suppose that the customers arrive at a Poisson rate of 1 per every 12 minutes, okay, and that the service time is exponential at a rate of 1 service per 8 minutes. So, lambda here is equal to 1 by 12 and mu equal to 1 by 8. Okay. The average number of customers in the system, just now we have seen the average number of customers in the system is given by lambda over mu minus lambda. So, LS equal to lambda over mu minus lambda, and this is 1 over 12 divided by 1 over 8 minus 1 over 12. So, we have 1 over 12 and we have here 24, and we get 3 minus 2. So, we get 1 over 12 into 24. So, we get 2. So, average number of customers in the system is 2. The average time a customer spends in the system, let us find the average time a customer spends in the system. So, average are expected time of a customer in the system, WS. WS is 1 over mu minus lambda. Okay. So, WS equal to 1 over mu minus lambda. Here the average time a customer. So, WS equal to 1 over mu minus lambda, and this is 1 over 1 by 8 minus 1 by 12. Okay. So, 1 over 24 and we have 3 minus 2. So, this is 24 minutes. Okay. So, 24 minutes is the answer. Now, we go to this last question on queuing theory. A supermarket has a single cashier. During peak hours, customers arrive at a rate of 20 per hour. Okay. So, arrival rate is lambda equal to 1 by 20, and the average number of customers that can be processed by the cashier is 24 per hour. So, mu equal to 1 by 24. Okay. Calculate the probability that the cashier is idle. When the cashier is idle, we have to find the P naught, okay, the probability that there is nobody in the queue, okay, in the system. P naught is equal to 1 minus rho. P naught, we found the formula for P naught. P naught equal to 1 minus rho, okay, and P n is the probability that there are n customers in the system. So, if the cashier is idle, there will be nobody in the system. So, P naught equal to 1 minus rho we have to find. So, P naught, okay, the first part is P naught equal to 1 minus rho, which is 1 minus lambda by mu, okay, and this is 1 minus 1 by 20 upon 1 by 24, okay. So, 24 divided by 20, okay. So, not like this. Here lambda is equal to we have to consider per hour, okay. So, lambda is equal to 20 and mu is equal to 24, okay. So, P naught is equal to 1 minus rho, and therefore, it is 1 minus lambda by mu, which is equal to 1 minus 20 by 24, okay. So, 24 minus 20 divided by 24, this means that it is 4 by 24. So, 1 by 6 hours, okay. So, probability is 1 by 6, okay. So, P naught is, this is 1 by 6, and then the average number of customers in the queuing system. Average number of customers in the system, we know average number of customers in the system is given by LS. LS is equal to lambda over mu minus lambda, okay. So, LS equal to this second part, LS is equal to lambda over mu minus lambda, okay. So, L lambda is equal to 20 divided by 24 minus 20. So, we get 1 over 4, okay. So, average number of customers in the queuing system is given by LS, and LS is equal to 20 by 4, 20 by 4. So, this is equal to 5, okay. So, average number of customers in the queuing system is 5. So, we have got the answer. Now, average time a customer spends in the system, okay. Average time a customer spends in the system is given by WS, which is 1 over mu minus lambda, okay. So, WS equal to 1 over mu minus lambda, which is equal to 1 over 24 minus 20. So, 1 over 4, that is 15 minutes, okay. This 1 by 4 hours, which is equal to 15 minutes, okay, 15 minutes. Now, then we have average time a customer spends in the queue waiting for service, okay. So, average time a customer spends, we have got, no, we have to first do this average time of customers in the queue, average time average number of customers in the queue. We can get from this formula WQ, WS we have got WS plus equal to WQ plus 1 by Q, okay. Average number of customers in the queue. So, LQ we have to find, LQ, okay. What is the formula for LQ? LQ is equal to LS, LS is equal to LQ plus lambda by mu, okay. LS equal to Ls equal to LQ plus lambda by mu. Okay. Ls we have found, Ls is equal to average number of customers in the system. Okay. Average number of customers in the system we have found, Ls is equal to 5. Okay. So, we have 5 equal to LQ plus lambda by mu, lambda equal to 20, 20 by 24. Okay. So, we have 5 by 6. So, LQ equal to 5 minus 5 by 6. Okay. So, 25 by 6, 25 by 6 means 4.1667, 4.1667. Okay. So, that is LQ. LQ is the average number of customers in the queue. Then average time a customer spends in the queue waiting for service. Okay. So, that means WQ is the average time a customer spends in the queue waiting for service. Okay. So, we have WQ. WQ is equal to WS minus 1 by Q, WS minus 1 by mu. Okay. WS be found to be equal to 1 by 4, okay, 1 by 4 hours, and 1 by mu is 1 by 24. Okay. So, this is 24 and we get here 6 minus 1. So, 5 by 24. Okay. So, 5 by 24 hours, that is to say 12.5 minutes. So, that is the average time a customer spends in the queue waiting for service. So, this finishes the discussion on queuing theory. Now, let us take an example on reliability theory. Consider an equipment or a system which is subjected to failure. Let Ft denote the probability of the equipment or system failure within t units of time. The system reliability RT is the probability that failure will not occur in t units of time, and thus we can say that RT equal to 1 minus Ft. Assume that a number of components are involved in the system. Let us consider two configurations, series and parallel configuration. In the series configuration, failure of any one component means failure of the system. In the parallel configuration, system fails only when all the components fail. Assume that in both the configurations the component fail independently. Now, this is the system in series configuration, this is the system in parallel configuration. So, there are three components C1, C2, C3 which are connected in series, and here there are three components which are connected in parallel configuration. So, let F1t, F2t and F33t denote the failure probabilities of the three components C1, C2, C3 respectively. R1t, R2t, R3t are the corresponding reliabilities. Then RIT equal to 1 minus FIT. I equal to 1, 2, 3. The system failure probability will be denoted by FST, and the corresponding system reliability RST will be then equal to 1 minus FST. Okay. For the series configuration, RST is equal to 1 minus FST is equal to 1 minus F1t into 1 minus F2t into 1 minus F3t. Why? Because the probability that the system does not fail before t units of time. Okay. We are looking at the probability that the system does not fail. We are finding the probability of the reliability. Okay. That is, the system does not fail before t units of time. So, and we are considering the series configuration. So, none of the three components must fail, and therefore, RST is equal to 1 minus F1t into 1 minus F2t into 1 minus F3t, because 1 minus F1t is the probability that the system component C1 does not fail before t units of time, and similarly 1 minus f2 t is the probability that the component C2 does not fail before t units of time, and similarly 1 minus f3 t is the probability that the component C3 does not fail before t units of time. So, their product then gives us the probability that the system does not fail before t units of time, and in the case of series configuration. Okay. So, for the parallel configuration, what will be the probability? FST is equal to 1 minus R1 t into 1 minus R2 t into 1 minus R3 t, because in the parallel configuration the system fails only if all the 3 components fail. Okay. So, 1 minus R1 t is the probability that the component C1 fails, 1 minus R2 t is the probability that the component C2 fails, 1 minus R3 t is the probability that the component C3 fails. So, when all of them fail, the probability will be given by FST, and FST is then equal, then FST gives you the reliability or probability of the system reliability, that is RST. RST is equal to 1 minus FST. Okay. So, in the case of parallel configuration, RST will be given by 1 minus FST, where FST is given by this product. Okay. So, now suppose let us consider an example. Suppose FIT is given by 1 minus e to the power minus alpha IT, alpha is greater than 0, I is equal to 1 2 3. So, FIT, as we have seen, FIT is the probability that the component C1 fails. Okay. This FIT is the probability of failure of the component. Okay. So, FIT is given by 1 minus e to the power minus alpha IT, that means F1 t is 1 minus e to the power minus alpha 1 t. This is the probability of the failure of component C1, and when you take I equal to 2, you get the probability of the failure of component C2, and when you take I equal to 3, you get the probability of the failure of component C3. So, FITs are given, and then the time t up to failure then follows the exponential distribution for the series configuration. We have seen in the case of series configuration, RST is equal to RST is 1 minus F1 t into 1 minus F2 t into 1 minus F3 t. So, we have RST equal to 1 minus F1 t, F1 t is 1 minus e to the power minus alpha 1 t, okay, into 1 minus e to the power minus alpha 2 t into 1 minus e to the power minus alpha 3 t, okay, and you get this expression. Okay. And for the parallel configuration, RST is equal to parallel configuration, RST equal to 1 minus FST. Okay. FST is given by 1 minus R1 t R2 t 1 minus R1 t into 1 minus R2 t into 1 minus R3 t. Okay. So, yeah, so we get in the case of parallel configuration. In the case of parallel configuration, RST equal to RST equal to 1 minus FST, FST equal to 1 minus R1 t. 1 minus R1 t is the probability that the first component fails, that is F1 t, F1 t into F2 t into F3 t. Okay. So, we get 1 minus F1 t into F2 t into F3 t. Okay. That is the system reliability in the case of parallel configuration. So, we have discussed both the cases. Okay. The system reliability in the case of parallel configuration and system reliability in the case of series configuration. Okay. And we have taken one example where we have taken particular values of the failure probabilities of the 3 components given by FIT equal to 1 minus e to the power minus alpha IT, where alpha is greater than 0 and I equal to 1 2 3. So, and we have found the values of RST for both the cases, the series configuration as well as parallel configuration. So, with that I would like to end this lecture. This is our last lecture on advanced engineering mathematics. Thank you very much for your attention.